Hello everyone, welcome to this short video that will explain to you red-black trees. We will have an introduction to such kind of trees. And what is red-black tree? Actually, it is a binary search tree, a special kind of it. So first of all, we'll explain binary search trees, and then we will introduce why we need a red-black tree and what are the criteria of red-black trees. So we will have some examples about this kind of trees and how to recognize a red-black tree. Then we will check the performance of such trees, and we will have a look to the insertion rules into these trees. Alright. In our outline, again, we will start with binary search trees, and that will show the need for balanced search trees, and then we will explain red-black trees, which is a special kind of balanced search trees, and then we will have the examples and we will see the performance criteria in red-black trees. Well, first of all, binary search trees are an ordered and sorted binary trees, and every node have two subtrees. The left nodes are smaller, the right nodes are larger. So, for example, in this tree, we have the root as 8. On the left side we have 5, which is less than 8. Then we have 7, which is on the right of number 5, and that's because it is larger than 5. But 7 is also less than 8 because it is in the left side of number 8. On the right side we have 10, so it is larger than 8, and that make it valid as a binary search tree. Then we have 12, and also it is on the right side of this node. Alright, let us go to the second example. In the second example, we can consider it as a binary search tree because every node have maximum 2 nodes, and every node on the left is smaller than the original node. So for example, we have number 8 less than 10, number 5 less than 8, so that's why it is on the left. Number 1 is on the left of number 5. What is the problem of binary search trees? Here, if I'm looking for number 1, it will take only 3 comparisons to find number 1. I will check whether it is less than or greater than 8. It is less than, I will go to the left side. Is it less than or greater than 7? If less than, I will go to the left, and here I find it. So I checked only 3 nodes to find number 1. So no need to check all of these nodes on the right side. While in the second example, we have to check at the beginning with, if I'm looking for number 1, I will check with number 10. Is it less than or greater than? If less than, I will go to the left. Then again, I will go to the left and to the left. And that will make us check all the nodes. So if I'm looking for number 1, actually I search and visit all the nodes in order to find number 1. So here we have a problem. Here we didn't save time because binary search trees is one type of these data structures that will organize the data. We want this data to be ordered in a way that I can search efficiently, or I can insert data efficiently, and so on and so on. And that will introduce balanced search trees. Such examples about these data structures are the AVL trees, the BL trees, the 2-3 trees, and the trees that we will discuss in this session, red-black trees. And that will make that any balanced search tree with n items will have a height of big O of log n. Alright, now we will see what are red-black trees actually. First of all, it is a self-balancing binary search tree, and it was a binary search tree, so all of the rules that we have explained previously, like that every node have maximum 2 nodes, the larger items will go to the right side, and the smaller items will be on the left side of the nodes, and so on. So these rules are to the red-black trees. Each node has an extra bit which represents its color, either it is red or black, so we have an extra bit for each node, and that bit will recognize the color of this node. Then we will have the properties. We have the root property, which is that the root is black. The external property, and here we have that all leaves are black. The null values are black. We consider them as black. The red property, if a node is red, then both of its children are black. And finally, the depth property, every path from a given node to any of its descendant null nodes goes through the same number of black nodes. So, for example, in this red-black tree, the root is black, and that will fulfill the first property. All the leaves are black, and that will fulfill the second property. And every red node have black nodes as a child, and that will make the third property valid. And the last property, depth property, we will count for every path how many nodes, how many black nodes we have. So for example, here we have 1, 2, and in this path we have 1, 2, and this path we have 1, 2, and 1, 2 for all of the paths. Now we will have another example to recognize this red-black trees. Let us see here in example 1. We want to check if this is a red-black tree, and in order to do this, we will go through the 4 properties of the red-black tree. First of all, we will check root property. Is the root black? In this case, it is not black, and the answer to is this a red-black tree is no, because the root property has been violated. Let's go to example 2. In this example, we are having the root as black. The external property, we will check all the external properties are black, then yes, alright. Red property, do we have a red with another red as a child? No childs as red. Now we will check the depth property. Are the paths having the same number of black nodes? Let us see. On this path, for each null, we will check how many black nodes we have. Here in the beginning, we have number 1, 2, so we have 2 null nodes and 2 black nodes from the null. Here we have the same thing, 2 black nodes from the null, while here we have 1, 2, 3 black nodes, and that will make a violation in this example. So it is violating the 4th property. Alright, now let us move to example number 3. In example number 3, we have these nodes, and we want to check if it is violating any rules. Is it having a black as a root? Yes, there is a black node in the root. All of the nils are black. Yes. Is there any red node having a child that is also red? There is no two adjacent red. Alright. The depth property, we will check all the paths for every nil node. So let us start from here this time. We have 1, 2, 3 black nodes in this path. And the same for this. 1, 2, 3, we have 3. And the same for this nil node, we have 1, 2, 3, 1, 2, 3. Now let's move on to this branch. We have 1, 2, 3, and for the second one we have 1, 2, 3. Let's move up. Over here we have 1, 2, 3 black nodes, 1, 2, 3 black nodes, 1, 2, 3 black nodes, and all of the properties are there, so no violation at all, and that will make this as a red-black tree. Alright, let's go to example number 4. Is this a red-black tree? We will check first the root property. Is the node black? Yes. Then we will go to the second, the external property. Are all of the external nil nodes black? Yes. Then we will go to the red property. Are all the red nodes having black childs? Here this node having a red child, and that will violate the red property, and that will make it as a non-red black tree. Alright, let us go furthermore. If we have any chain of 3 nodes, then definitely this will violate the depth property. If we have like black, 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 then from this side we will have 4 black nodes, while from here we will have 3 black nodes, and from here we have 2, so different number of black nodes for each path. And if we have only 1 red, we will have, yes, 1, 2, 3, and here we will have only 2, and here 2, so 3 black nodes on this path, while here it is 2, and that will violate the depth property. And if we consider having 2 adjacent red, that will violate the red property, and that will cover the whole probabilities of the chain of 3 nodes. Now we will check the performance of this type of data structure. When we are going to use the search, finding minimum, finding maximum, the successor and predecessors, we will follow the big O of log n time when we use the red black tree with n nodes. Alright, in next video we will explain the insertion. We will go through the rules of insertion, like if tree is empty, we will create a new node as a root node with color black, and if it is not empty, we will create a new node as a leaf node with color red, and if parent of new node is black, then we will exit, and so on. That will be added next video. Thank you for watching this video. Hope you understand now what is the red-black trees.